Okay, yeah. So yeah, it was first given by the crystal base for that representation was given by the Bankart, Kang, and Kashwara. And then I will talk about another family of indecomposable representation, not formal module, still finite dimensional representation called the CAS module. Of course, I will think about its Q deformation, and then talk about its crystal base theory. And then finally, I will talk about the negative half of the quantum group of GLMN. Of course, it's a crystal base. Okay. Okay, so let me start with the first section about quantum superalgebra. Okay, let me start with what is Lie superalgebra first. So our base field is the complex numbers. And then, yeah, the superspace means Z2-graded vector space. It's just the sum of two homogeneous space V0 and V1. So we call this space the even, and this one is odd space. And then we think of this endomorphism algebra over the complex numbers, and then say GLV, which is also a superspace where depending on the degree of the linear map. So the degree epsilon linear map F means by definition it sends the homogeneous space V sub kappa to the epsilon. Okay. So it becomes a superspace, and then we want to give a Lie superalgebra structure by using the supercommutator. So here, so usual commutator is Fg minus Gf, but now we twist by sign depending on the parity of the homogeneous map. Okay. Then with respect to this supercommutator, GLV becomes Lie superalgebra. Of course, I didn't give a definition of Lie superalgebra, but okay, so it has a super skew symmetry and also it satisfies so-called super Jacobi identity. But it doesn't, we don't use that definition, so I will skip the definition here. Okay. Let me give a more explicit form of GLV. So for this, we want to think of this matrix form. So for this, we have to fix the basis of the natural representation where GLV acts. So we fix the two non-negative integers throughout my lecture, say m and n, and then we consider the index set, say I, m/n. So it is m plus n elements with a linear order, usual natural linear order. But here we give a Z2 grading on this index set. So first m integers are even ones and the other ones are the odd ones. So I use the colors. So blue. So usually in my lecture, this light blue means the even ones, and this light red or pink ones usually means the odd ones. Okay. Then we consider the superspace, C to the m/n, where the even part m/0 is spanned by the basis element parameterized by the first m elements in our index set, say I, m/n, and the other space is spanned by the basis from index from this odd one. Then with respect to this standard basis, then we can think of this matrix form of GLMN. So say, so GL of this superspace, we usually denote it by GLM/n. So it is just a space of m plus n by m plus n matrices. And we can think of this block matrices. And the diagonal m by m and m by m matrices are the homogeneous of degree 1, 0, and the other off-diagonal block elements are odd ones. Okay, and some basic fact is that if we consider only the even homogeneous subspace, then you know that it is isomorphic to the direct sum of two GL, general linear Lie algebra of rank m and n. Okay, so this part is trivial. And the H means the Cartan subalgebra spanned by the elementary diagonal matrices. Okay. Okay, then we can think of so in super case we can think of a super trace. Super trace means the sum of the diagonal entries, but we take a minus or multiplying minus on the last n elements. So with respect to this super trace, we can think about the non-degenerate invariant supersymmetric bilinear form. And okay, so kind of an analog of Killing form. Then we think of a dual basis, say delta A, dual to this Cartan basis of a Cartan subalgebra. Then we consider the induced bilinear form on this dual space spanned by the delta A. Then we can observe that unlike the usual case, it's a almost orthonormal basis, but there is a sign. So for the first m elements, it's orthonormal basis, but the other elements actually the norm is minus. That's the difference. The first difference when you consider the super case. Okay, and also we can. So now we are considering it's a matrix realization, and then with respect to Cartan subalgebra, we can think of it as a root system. Then, as you may notice, that there's no difference compared to the usual type 8 root system of rank n plus n minus 1. Yeah, so the positive roots are spanned by this, in terms of this delta basis, the delta A minus delta B. Yeah, this is the set of roots, and if A is smaller than B, then it gives the set of positive roots, and the corresponding root vectors are just the elementary matrix corresponding to these two indices, say A and B. Okay, and now our Lie algebra is basically Z-integrated, so our set of roots are divided into two sets. One is the even roots, and the other is a set of odd roots. So the even roots is the roots of the even part, the GLM and GLN. So our positive even roots are spanned by this difference where the two indices are of the same parity. So both even or both odd. And the odd roots are the spanned by these pairs where they have two different parity. Okay. And of course, if we have a system of fundamental system or the set of simple roots, looks like the same as in the case of usual type A. So it is delta A minus delta A plus 1. And also we can think of the thinking diagram. Then so here in this case, our thinking diagram looks like this. And so so most of the roots their norm is 2 or minus 2. So minus 2 happens because the delta A its norm is minus when the index is odd. So for that case, we have even roots with a negative norm, which is actually minus 2. And we have also even roots with the positive norm, so 2. And there is one odd simple root, which is corresponding to the index m and n plus 1. And in this case, the norm is 0. So it has an isotropic simple root. So that's the main difference from the case of a usual simple Lie algebra of type A. And this actually gives, how to say, so in case of a simple Lie algebra, from the root system, we can think of a reflection with respect to any positive root or a simple root and think of its Weil group. But in case of super case, there is a simple root with isotropic with its norm 0. So not all the simple roots give the reflection. So the combinatorics of Weil group is not enough to study the representation of a Lie superalgebra. Okay. Okay, so, but anyway, in general, for any given Lie superalgebra, there is a notion of enveloping algebra or Lie superalgebra, which is defined in the same way. Now we consider the supercommutator. Okay. And one fact I'd like to mention is that, so let's think about the positive part of GLMN and its enveloping algebra. Then we also have a PBW type based theorem. So this subalgebra decomposes into the two subalgebra, even and odd, and this is nothing but the enveloping algebra of the GLM plus GLN is positive part. And this part is, so we have an odd root. And in this case, any two odd root vectors, if we take the anti-commutator, then it's just a zero. So in the enveloping algebra, the commutator, anti-commutator of two odd root vectors is just a zero. So they are just anti-commuting. So as an algebra, is this part, the red part is isomorphic to the exterior algebra generated by the odd root vectors. So the positive part of our Lie superalgebra looks like this. So the usual ones and some exterior algebra is tensored. Okay. That fact is needed when in the second lecture. Second lecture. Okay. So now let me introduce this quantized enveloping algebra. So yeah, so we consider for a formal variable Q, we consider is the field of rational function. And then there is a Q-deformed enveloping algebra for the general linear Lie superalgebra. As far as I know, it was first introduced by the Yamane. It's already more than 23 or 4 years ago. So its definition is very similar. So we have Chevalier generators corresponding to each simple root. And now since we are considering general linear, so Gartang part is generated by the parameter is from the basis of the natural representation. Okay, so Ka, and the relations are very similar. So the yellow ones are the almost the same, and the only difference is here when we consider the y relation, we have to consider is a sign depending on the parity, and also there is some sign. That's a technical definition. And for the Chevalier generators corresponding to the even simple root, whether they are positive or negative norm, they satisfy the usual set relation. Okay, and plus there is an additional relation. Let me say the odd set relation, which is involved which is related to the generators for the odd isotropic simple root. Yeah, I'm not going to write down the relation because we are not actually using that one. But anyway, it's not very complicated, but there is extra relation. That's the point. Okay, so of course, we can think of its classical limit. So it goes to the usual, under a suitable setting, it goes to the usual enveloping algebra of GLMN. Okay. Yeah, but I want to give some couple of comments. The first is, yeah, so the usual quantum group, SL2 triple or the UKSL2 triple, it plays a, even in case of quantum group, it plays the important role. So, but anyway, I want to comment that, so for each even simple root, we can think of as UKSL2 triple. And for positive norm, the same as the usual one. And the negative norm, in case of negative simple root, if we look at the defining relation, then it is isomorphic to the UKSL2. But in this case, the parameter is replaced by the Q minus 1. That's the difference. And this algebra can be viewed as a Z-graded one, where we define the degrees for the generators For the odd simple roots, the corresponding Chevalier generator has degree 1, and the other generators have degree 0. So it gives us integrated algebra, or sometimes super algebra. So we can think of a super representation. But in my case, or in my lectures, actually super representation doesn't play a very much important role. So I want to think of representation as a usual representation of a usual algebra. But anyway, we need to translate the terminologies. So instead of a super representation, we can equivalently think of replace a super representation as a representation of a certain twisted group algebra of our UQGLMN. So that means okay. So we consider the order 2 abelian group generated by sigma, and then we consider twisted group algebra with the coefficients from UQGLMN. Then the relations are given by this one. So they commute, and then and for the other generators, there is some sign appears. So what I want to say is that considering a super representation of UQGLMN is equivalent to a usual representation of this twisted group algebra. Actually, this order 2 elements actually, when they are acting on the representation, then if we consider its eigenspace decomposition, then actually gives Z2 grading. Okay. Yeah, that's what I just mentioned. So we want to consider UQGLMN sigma module, and it's Z2 graded. So the sigma is diagonalizable, so it is Z2 graded. So it is equivalent to saying a super representation of UQGLMN. And also there is a Hopf algebra structure of our twisted group algebra. Sorry. Yeah. Sig D. What is D? Yeah. 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 So is there any typo in the Hopf algebra structure? Oh, I see. Power over sigma here. There must be some power. Oh, I see. Yeah. Oh, sorry. So sorry. Yeah, there should be the parity of alpha. Okay. Sorry. Thank you. Thank you. Yeah. Yes. Yeah. Sorry. And thank you very much. Yeah. Okay. And okay, so my weight lattice is the free abelian group generated by this delta A, and our weight space of V is the space where the K mu came. So here, so mu from P and K mu can be defined in a natural way. So our weight space axon is defined in this way. So it's the same as in the usual quantum group case. Then, okay. And one more remark is that instead of the usual quantum superalgebra introduced by Yamane, I want to use, I'm going to use another version of a quantum superalgebra. So due to Kuniba, Okado, and Sergeyev introduced in more recently, and it was, yeah, interestingly, it came from their study on the three-dimensional Yang vector equation on and algebra of symmetries related to that. but essentially the same object. But there is some reason for why I prefer this the convention. And sorry to Professor Yamane. But anyway, so okay, so I will use. Let me briefly introduce this convention. Okay, so first we use. Let me introduce this kind of Q variable, Q sub A, parameterized by our index S. So when index is even, then Q, and the other case minus Q inverse. So basically I want to how to say, to control more easily the minus signs when you study the superrepresentation. Okay, and then instead of Q to the bilinear form with the two weights, I will introduce another function, bi-additive function on the weight lattice, where for a given two weights lambda and mu, with this linear combination, then we define this function to be the product of Q sub A to the product of the coefficients. So when the index is all even, then it's just the usual Q to the lambda paired mu. But I will use this function instead. So naively speaking, the effect of this change of convention is that actually the parameter Q when acting on, or the Q coming out when it considers the action on the odd space, we replace it by minus Q to the minus 1. So this is just somehow the technical one, but there is some benefit. But anyway, and so I didn't give a definition for the other version of quantum superalgebra. But anyway, it's almost isomorphic to the UQ-GLMN. So they are not actually isomorphic, but somehow if we extend by adding some generators, then there is an algebra isomorphism. So we consider some kind of the degree 2 generators parameterized by this index set, which are commuting, and also have the same very similar relation as in the case of the sigma in the previous slide. Okay. Then yeah, it's also can be viewed as a twisted group algebra with coefficient of UQ-GLMN. Oh. Yeah, so I have to say. So Kuniba, Okado, and Sergeyev's version of the quantum group is defined in the same way as in UQ-GLMN. Only difference is in the defined relation, we replace this kind of things to this one. And that's the definition. And so we have two versions of quantum groups, UQ by KOS and UQ by Yamane, and we extend it by considering the twisted group algebra. And then there is a K-algebra isomorphism, where each Chevalier generator is mapped to the Chevalier generators corresponding to the same simple root, but there is some product of the group elements. That's the only difference. And when you consider the action of this algebra, for example, if we consider the representation of this quantum group and then pull back the action of this algebra to this one, then the weight space here exactly replaced by the weight space where the Q function is replaced by this bold Q function. And okay, and also, so now I want to use the quantum group on the left-hand side, and also I will use the co-multiplication of this another version, the usual, the defined here as follows. So it's the same as the usual quantum group version. Of course, I have to mention that under this isomorphism, if we pull back this co-multiplication to the right-hand side, then it does not coincide with the usual co-multiplication on the Yamane's version. And also, yeah, so if we equivalently, if we pull back the co-multiplication here, then it doesn't give the same this co-multiplication. So somehow I used a different co-multiplication. But the advantage here is that on the left-hand side is that many of the arguments in the usual quantum group can be applied directly by this in terms of by using this change of convention. Yeah. Okay, so that's the introduction of the quantum superalgebra. Okay, so next I will talk about some special family of finite dimensional representation of the UQ shell MN, so the Kuniba Okado Sergeyev's version. So let me just denote it by from now on U sub MN. Okay. So the first thing I have to say is that, of course, I have mentioned at the very beginning of this talk. So unlike the case of the usual semi-simple linear algebra or its quantum group, in general, a finite dimensional UMN module is not semi-simple any longer. But if we think about the crystal-based theory for the irreducible representation, then it is well established in case of the integrable case. So where they are semi-simple, where it is a semi-simple and also the tensor category. So instead of considering all the finite dimension representation, we will focus on some good family of representation, which forms a semi-simple tensor category. And actually, there is such kind of things which are due to the Chauvel and the Zimbo duality. So yeah, so in case of GLM, so there is a Chauvel duality, and also there is a Q analog, and also there is a M/N version of the Chauvel duality, and also it's a Q version. So let me introduce more precisely what kind of irreducible representation appear from this duality. So now we focus on more special type of weight, say P non-negative. It's a semi-group generated by our basis delta A. So let me call it the set of polynomial weights. The all non-negative denote the category of UMM module with weights in this polynomial semi-group. Okay, then as you may expect, then we start from the natural representation of GLMN or the Q analog. So it should be M/N. Okay. So it has a basis parameterized by our index set, where each one is connected by the Chauvel generators, and each VA has a weight delta A. So it is a very basic example of the polynomial representation, or in our category. And also its tensor product also belongs to this here. Okay, so then there is the well-known, very famous Chauvel duality, or is the Zimbo's Q analog, holds in this case as well. So if we consider the D tensor power of our Q analog natural representation, then of course there is an action of our quantum group. And also there is an action of the Hecke algebra of type A of D-1. And they form a double centralizer. They satisfy double centralizer property. So it is a semi-simple UMM module. So we are interested in the irreducible representation appearing here. Of course, it is a highest weight module, so we need to characterize its highest weight. Okay, so for actually it can be combinatorially described. So for a given partition, we want to impose this kind of condition: lambda n plus 1 is less than or equal to n, so-called M and Hook partition. The reason why we call it hook is that if we consider it's a Young diagram, then it fits into the hook of size m and n. Okay, so then for each hook partition, we consider a weight, say capital lambda, sub lambda, by determining the coefficient of each basis by from our partition lambda, and the first n parts given by the first n parts, the coefficients are from the partition, and the other parts are the coefficients are from the conjugate of the other parts of our partition. So for example, when m is 2 and n is 5, then this partition is a 2-5 hook because it fits into this hook. Then we determine the weights in this way. So first m part, the even part, we fill the first row with 1 and second row with 2. And then in the remaining part, we fill the diagram, Young diagram, in vertically. So the 3 is filled with the first row. The first column is filled with 3, and the next one is 4, 5, 6, 7. And then we count the number of each eyes appearing in this Young diagram. Then the weight is determined. Okay, then we consider the irreducible highest weight representation of UMN with highest weight capital lambda. Of course, our quantum group has a triangular decomposition, so we can think of it as a Bowman module and its maximal quotient. So highest weight irreducible highest weight module is well defined, so we can define this one, parameterized by the M&Hook partition. Then by standard arguments, then we can show that this D tensor power is decomposed into the tensor product of this V lambda tensored by the Specht module of the Hecke algebra. The first part, it can be proved by standard arguments, and then following the usual Chauvet duality, I mean. And the second part was one of the main results in the Bankert, Kang, and Kashwara in 2000. And actually, they show that their statement is more general. But anyway, so you can check that every irreducible object in this category, so the polynomial weights, is isomorphic to this simple module, parameterized by lambda. And of course, there is a combinatorial model for the character of this simple module. As in for GLM case, usual general linear case, the character of the finite dimension irreducible is described in terms of the Young tableau or semi-standard tableau. So here in this case, we have the super analog, say M&Hook semi-standard tableau. Maybe this notion was first introduced. I'm not quite sure. So one of the reference people know is introduced by Beryl and Regev. So anyway, we can think of M&Hook semi-standard tableau. That means, so it is a semi-standard tableau where the alphabet are from our index set. And this index set has Z2 graded. So for the degree 0 entries or alphabets, they satisfy the usual semi-standard rules when we define the Young tableau. And for the alphabets from the other degree, they satisfy the semi-standard rule with transpose 1. So they are weakly increasing along the column and strictly increasing along the rows. Then the character is of this set is equal to our irreducible representation. And this is also often denoted by Hooke-Shaw polynomial. And some people show polynomial. Yeah, then it is proved that this irreducible representation has a crystal base with crystal structure. It's actually isomorphic to the set of semi-standard tableau, Hook semi-standard tableau of shape lambda. But I didn't define the crystal structure on this combinatorial object. But anyway, their crystal is actually described in terms of those super analog Young tableau. Then maybe I have to say that what is the crystal base here? What is the definition here? Okay, so it is defined in a very similar way, but yeah, the formal definition that looks like the same, but the only difference is why is the crystal operator here? So the crystal operator, it depends on on the parity of the simple root and also the sign of the norm of the even simple root. So when the simple root is a positive norm and also it is even, then the crystal operator is the usual lower crystal operator. So the lower crystal operator is maybe the in many papers, usually the lower terms, people don't how to say it. The usual crystal operators in many papers are the lower crystal operators. It is compatible with the lower co-multiplication. And for the even simple root with a negative norm, then we define the crystal operator in this case as an upper crystal one. So the upper crystal operator is basically compatible with the upper co-multiplication. And last, when for the other isotropic simple root, the crystal operator is defined just by multiplication by the Chevalier generators. And the reason for this is that actually, if we consider the triple, the subalgebra generated by E alpha and F alpha and K alpha, which is the Q analog of the superalgebra GL11, then basically their simple representation is trivial or two-dimensional. So the graph, if we only consider the graph with respect to this other simple root, then the crystal graph is just the single point or the only one arrow. Okay. Then why should we define in this way? So let me explain the reason for this definition. So here's a remark. Okay, so we only need to consider for the even simple root with the negative norm. So as I mentioned before, this subalgebra generated by this one, then it is isomorphic to, so in our convention, this algebra is isomorphic to the UKSL2, but the parameter Q is replaced by minus Q inverse. So the isomorphism is given by this one. So E to the E, F to the F, K to the K, but the Q is just replaced minus Q inverse. So if we want to think about the crystal at Q equals 0 on the left-hand side, then it corresponds to the crystal at the parameter P is infinity. And here the co-multiplication is the lower one. So if we translate it into at P equals 0, then we have to apply the bar involution. Then the corresponding co-multiplication becomes the upper co-multiplication with the sign order is flipped. Okay, so this crystal operator, if we want the crystal operator here, then actually it corresponds to the upper crystal operator. That explains why we have to consider upper crystal operator. And also due to the flip appearing in the co-multiplication, so the co-multiplication here should be the upper crystal operator, where the tensor product with is the same, but here the tensor product order is reversed. Yeah. That's what happens when you consider this GLMN case. There's another equivalent explanation for, yeah, so Yeah, there's another, if we take this kind of isomorphism with the UKSL2, then e to the minus e, f to the f, k to the k inverse. So there's a change of co-multiplication. So lower becomes the upper one, and the order becomes reversed. That's why we have to consider the upper crystal operator. Okay. I think that's enough to give a conceptual understanding when you study there. When you first study the crystal base theory for super case. Okay, so with respect to this crystal operator, we can define in the same way the crystal base for any given representation. So it is a pair of A0 lattice and some pseudo bases, AQ equals 0, and it is invariant under our operators. Of course, there is some compatibility with the weight-based composition. Okay. Yeah, then with this more precise definition, then it was shown that the irreducible polynomial representation phi of lambda has a crystal base. And furthermore, in the same paper, it was shown that one of the powerful theorem in the crystal base theory is that the tensor product theorem. So here they also showed that the tensor product of two crystal bases becomes a crystal base of the tensor product. And also what is good is that there's a very explicit combinatorial rule for the crystal operator. Yeah, so for the even simple root, whether it is positive norm or negative norm, we already know the tensor product rule. Whatever it is lower or upper, we already have a tensor product rule. And the only difference is that when you consider the upper crystal operator, the tensor product order is reversed. And for the case of other isotropic simple root, the crystal operator on tensor product is very simple. So when you apply this f alpha tilde to this tensor product, it acts on the first component when the weight of the first tensor factor has a non-trivial pairing with this simple root. Otherwise, it goes to the other tensor component. So if we apply this operator to more than 3 terms of tensor product, then this operator goes to acts on the first component if it has a non-trivial pairing. If not, it goes to the other factor. Also, if it doesn't have a non-trivial pairing, then it goes to the other factor and so on. Yeah. And basically, the Bankart-Kang and Kashwara's proof of the existence of crystal base for the irreducible polynomial representation was a rather inductive process inside the crystal lattice or crystal base of the tensor power, the natural representation. But eventually, it turns out that the crystal base for that irreducible polynomial representation is also equal to the crystal lattice is also spanned by the A0 lattice, A0 span of this kind of monomials, where we start from the highest weight vector, and then we apply finitely many times where x is E or F. Then the A0 span of this kind of monomial gives the crystal lattice, and its image at Q equals 0 gives the pseudo basis. Yes. F. Yes, right. So here in this case, we have to consider E and F both. If we consider only F, then we are not guaranteed that. Yeah, that's actually important point. So still, as in the case of Kasumuri algebra, the crystal of the irreducible polynomial representation, it is connected. So it can be generated from the highest weight vector element, but not only applying the F alpha tilde. So we have sometimes go to apply E alpha tilde as well to get the whole graph. Yeah, and yeah, so the proof where the crystal of this irreducible polynomial representation is isomorphic to the crystal of this semi-standard Young tableau. Yeah, so I have to say that this has an abstract crystal structure by starting, so it can be defined inductively applying the tensor product rule. So if you are familiar with the crystal-based theory of the usual Casimir algebra, then it does the way we define the crystal structure here is the same as in the case of the usual Young tableau. We start from the natural representation, and then we consider the tensor product. And then for each tableau, we read the entries of the tableau in certain order. Then we embed this word into a tensor product of this crystal of the natural representation. Then is well-defined. It has a well-defined crystal structure. And then actually it is shown that it is isomorphic to this crystal. Okay. Yeah, and then this part is related to the question just before. So we may have an element B such that which is not V lambda, not the highest weight element, but it is still annihilated by all the E alphas. So it was called a fake highest weight vector in the Benkar-Kashua's paper. Yeah, so that's one of the difficulties when you study the crystal structure here. And also, the other difficulty is that unlike the case of the usual gel M crystal, say Bm of lambda, how to say? So, yeah, so there is no natural crystal embedding for two Hook partition or the associated integral weights, highest weights. How embedding of the crystals between these between crystal of the two irreducible ones. Yeah, for in case of gel M, so there is a natural partial order on the set of dominant weights. So and there is a natural embedding of the crystal of the highest weight crystal. So we can take a natural limit of that abstract crystal, and then eventually we can show that it is isomorphic to the crystal of the negative half of the quantum group. That's the story of the gel M or the Casimir algebra case. But here in this case, as far as I understand, then even it is not how I don't know the natural partial order on the set of Hook partitions, which gives embedding of a crystal associated these two height. So yeah, so of course there is a insertion scheme for the Hook semi-standard tableau, which is compatible with the crystal structures, but no natural embedding of the two highest weight crystal. That's why it is difficult to think of a crystal of the negative half of the quantum group. Okay, I will talk about how to overcome this difficulty in the second lecture. Okay, so now I have 9 minutes. So I will give some examples of the crystals. Okay, so the first one, so here we assume that M is 3 and N is 4. So this one is the crystal of the natural representation. Here the odd isotropic simplest acts on these two different parity elements. And in general, okay, so now let us consider more general case of semi-standard tableau, say shape is 5, 3, and 2, 2. So M is 3 and N is 4. So the first 3 letters satisfy the usual semi-standard condition. So weakly increasing and strictly increasing. And for the last 4 elements, they satisfy the transpose semi-standard condition. So it is actually weakly increasing, but they are all strict. But anyway, and also here in this way, they are strictly increasing. And the crystal structure here is given by reading the entries of this tableau. So in my case, I choose the row reading. So from the first row. Yes. 6, 3. Yes, that's right. Yes, right. Right. Yeah. 2 here. Okay. The other elements all they have 2. Okay. So anyway, so suppose that there is one more 2 here. Okay. So our word is like this one, and then okay, and then it has a.
I think be slightly neat, but the semi-standard tableau shape needs to change too.
Oh yeah. It's +1. Okay. Yeah. Okay. Thank you. Okay. So here we have a word, and each letter belongs to the crystal of the natural representation. Then the whole word belongs to the 12 tensor power. Then we apply just the usual signature rule. Many of them are familiar with it, I think. But anyway, so if we apply the F1 tilde, which has a positive norm, then only 1 and 2 alphabets are involved, and we assign the plus and minus sign. Then we read the sign from left to right. And also we have some cancellation rules. So here we erase plus and minus. So the only the signs which has meaning here is the minus, -2. So we change this minus to minus. Okay. So now we consider the case of the simple roots with negative norm. So in this case, 4. So letters 4 and 5 are involved. So 4 has a positive and 5 has a minus sign. And then we have a sequence of plus and minus. And then now we read the signs from right to left. Here in this case, it should be, this pair should be erased. So the F4 tilde acts on this 4, changing it to 5. Okay. The other simple root, yeah. So the 3 and 4. So here is the 3, which first appears when you start from the leftmost one. So we change simply 3 here to 4. Yeah, I mean, and the first lecture with a couple of applications. So our quantum group has only one odd isotropic simple root, and that is related to our choice of the Borel or the set of simple root or the simple root system. But if we change the Borel, then okay, so the first case is that's not my first choice. Okay, anyway, we can, so our index set I_m/n is the parameterization of the natural representation. So we start, so this lecture, I chose the parity. The first m letters even and the others are odd. Then actually that kind of arrangement of the signature determines the simple root system. Now we can shuffle those elements where the parities are the same. Then for example, if we consider the index set, so maybe, so following the notation in the beginning, then maybe I can choose the arrangement of the index 5, 4, 6, and then 1, 2, 3. Then the corresponding root system or simple system or the thinking diagram is the same. But if we shuffle like this, as in the second case, where the parity of the letters are alternating, then the corresponding simple root system or its thinking diagram looks like this. So all the simple roots are odd, isotropic. So there is so we can think of a quantum superalgebra generated by the Chevalier generators associated to this fundamental system. Also, there is the definition for this simple root system. So we can think of the crystal-based theory with respect to this quantum group or the presentation. Okay, then we can think of it. And one application was that in one of my previous work, I considered only the abstract crystal level. But anyway, I consider the crystal structure of the tensor power of the natural representation with respect to non-standard choice of simple system. Then I found that there is some connection with it has a connection with not with the Hooke-Shor polynomial, but with the quasi-symmetric functions. Yes. So just a short remark. And also we can think of a crystal-based theory for the quantum affine superalgebra. So, for example, we may think of the quantum affine superalgebra of type A with respect to this thinking diagram, where the underlying finite type is the same as in this lecture, but we add one more. The simple root system. Of course, there are other. We may take the other simple root system as well, but this is one of the standard ones. Then recently, in a joint work with Professor Okado, that we actually constructed the Killow-Thresh-taken type module for this quantum super, and show that it has a crystal base, and the underlying set of the graph can be realized in terms of the Eman-Hooke semi-standard of a rectangular shape. And also we can describe very explicitly the crystal operators for the extra additional simple root. Yeah. And finally, so then some comments about the crystal for GLMN. Then so far the question is, one may ask whether there is other crystal realization. For example, in case of Casimir algebra, there are many combinatorial models. Some of them are specified to the type of the Lie algebra, but some models have a very uniform realization. Doesn't depend on the type. For example, the Lakshmi-Barish-Chaudhry's path model. So it is natural to ask whether there is other combinatorial model for the crystal of GLMN. But so far, I don't know whether there is other known results on this problem. And the more interesting problem is that whether there is a global crystal basis or a canonical basis for the irreducible polynomial representations. There are a couple of works related to this one. So using for example, using the Q analog of the Chauvet duality of the superversion, then from using the canonical basis of Hecke algebra, then we can naturally define a kind of a canonical basis of the tensor power of the natural representation. But but I don't know whether there is another construction of the basis, natural basis for this irreducible polynomial representation, which is compatible with the crystal base of the Benkei-Khan Hashiwara, and also have some very good properties, which is related to some structure of this irreducible representation. And yeah, I think that the one of the difficulties of the existence of the canonical basis of this irreducible representation is that there is no presentation of this irreducible representation. So I mean, for the GLM case, there is a well-known presentation of the irreducible representation with finite dimensional irreducible representation. But even for GLMN and even for the polynomial representation, then there is no presentations now. So that's I think that is related to the difficulty when you try to find the canonical basis of this irreducible representation. Okay, so let me stop here. Yeah.
Thank you very much. So are there any questions or comments on this talk? Yeah.
There's some sort of general definition theory that tells you how rigid, like how many different kinds of tunnels can make from.
Is there a Drinfeld kind of deformation theory that tells you how rigid, how many possible kinds of quantizations of these kinds of least superalgebras there are?
I don't know. Yeah. I know. But one thing I can say is that even for the same least superalgebra, there we can choose the different. We have a different choice of fundamental system or a set of simple roots with different thinking diagram. But there is isomorphism actually. Yeah. But yeah, but I don't know the answer to your question. Yeah.
Are there any questions or comments? No. So can I ask one ordinary question? So are you surprised that there is not yet LS path model for this algebra GLMN? So could you explain why there is not yet such an LS path model for this algebra?
Yeah. Yeah, as far as I understand, the LS path model is the model which best explains the modular character formula or the modular filtration of the irreducible representation. And so far, no modular character formula or the modular solve module of this superalgebra is known. Yeah, actually, yeah. So I prepared some extra slide. Modular character. Yeah, the reason why I didn't introduce this slide is that there might be some misunderstanding of myself. So it's, but anyway, it's an important question whether there is a kind of. So basically, we can think of a maximal vector. We start from highest weight vectors, and then on applying the y group action, then we start from. Then we consider certain external vector, and then consider the Borel action, then consider certain solve module. Then nothing is known about the character formula for such a kind of things. So the reason why the lattice formula is not known is that problem. And then I just want to mention some the character formula. There might be some misunderstanding. So don't trust too much this slide. Say there must be some typo. So please turn off the YouTube. It's just anyway. So there is a maybe if you read the book by the McDonald, there is some exercise or example that there is some interesting formula, the Hooke-Shaw polynomial, due to the Sergeev and Pragas. And yeah, it's given by the certain symmetrizing certain factor given by certain factor. So this part I couldn't check 100% this morning. But anyway, so if we look at this part, then maybe we can think of a certain partial sum of this character formula. So replacing the whole symmetrizing part by taking some partial application of the divided difference operator. Then yeah, one may ask whether it actually gives a character formula of the De Morgan module, but yeah, it's not known yet. Yeah.
Thank you. So are there any questions? Oh,
Yes.
Sorry, I'm thinking of these dumb questions. So what kind of Lie superalgebras have quantizations? Is there some sort of characterization of them? Or
For example, yeah, so the GLMN in this lecture, and also there is another important class, finite dimension simple, OSP, also simplex Lie superalgebra. So it's kind of mixture of BCD.
so are you giving examples or a complete list?
Example of
I'm asking what axioms do you need on your Lie superalgebra so that it has a quantization?
what?
Is any theorem like that known? I just don't know anything about this area.
Yeah, I think I don't understand your question completely. Fully. Yeah.
So I just like, Casimir, they all have quantization.
Yeah, there is a quantum group for. So I mean the quantum group of a kind of superalgebra you're asking.
So let me try and translate.
Okay.
I understand your question and I understand.
Yeah.
So my understanding is all Casimir superalgebras have quantum groups associated to it, but there's no axiomatic way. So Qn does, OSP does, I believe, to have a corresponding quantum group. But and very recently, the Perry Collective had a quantum group constructed like a year or so ago, but
Mhm.
there's no universal general construction.
Oh, yeah,
Like
no.
all of the basic ones, I think, like
Yeah.
all like the D4 alphas, I don't think there is one itself.
Katsumori super and finite dimension simple Lie superalgebra, as far as I understand, is a different direction. Yeah.
I will say a comment.
Yeah.
I say just very clear that you don't find answer that may not be an answer you asked. But I would say that firstly, historically, Katsumori algebra is defined by same relation. It is defined in actual way, just written in third page of textbook. In a similar way, quantum groups can be defined in a similar way. Just technique for using universal matrix using pairing, natural pairing, quotient, taking place quotient radical. In such a way, we can construct for any Katsumori, any controllable superalgebra, we can define associated quantum superalgebra. Yeah, that's what I would say.
So can you construct kind of like an alcove, well, I guess maybe more like a building and apartments for GLMN? kind of related to the LS path model and trying to build like an alcove path model, but somehow,
Yeah.
I mean, dealing with the odd reflections, I know is kind of the problem here, but if there's a way to do that.
I have no idea. Yeah.
Right.
And
Thank you.
one of the difficulty might be the phi group is not enough for the super case because of the isotropic sample rate. Yeah.
Right, yeah, I was wondering if you'd seen anything related to because a way you can construct buildings is from the Lie group. And then you look at the spherical apartment and sorry, not the spherical, the affine apartment.
Mm.
And that's basically your alcove picture. I was wondering if something similar could be done here with the corresponding Lie super group. So,
Mm.
yeah, thank you.
Yeah. Some people think of the notion of a group point when it considers the super case to overcome or how to that problem. Yeah.
I studied while group.
Oh yeah. Yeah.
In the collaboration work with Ishan Ekebara.
Yeah.
But Yamuson saying that it is not essential. More essential to work group recently introduced by LBA and I hope so. Yeah. Anyway, very famous person, very famous paper published by Arnold. They call it a super wide group point. It is
Yeah.
different from
Yeah.
our group point in Hekebara. But
Yeah.
anyway, quite recently, Youngson published put up preprint in an archive many in a few months ago. He called their group point just one group point.
Mhm.
But originally, the original person called it a super wide group point. Yeah.
Okay. Thank you. Yeah. Yeah. Thank you. Yeah.
Other in comments or questions? No. If not, let's thank the speaker again. So the next talk will start at 3 p.m.